Good day to you. This is Anagalactic bringing you another presentation in cosmic science. Different approach today. I would like to show you the effect upon our perception of geometrical physics. If I were right, what if this geometry that I claim to have discovered were actually validated? What would that entail? What kind of changes would that entail? I'd like to give you a star creature's overview, some universal creature just looking at the universe going in from the outside. What would be different, assuming we could take a human perspective, Gedankenexperiment, what would be the value of knowing spherical geometry, which I claim has never been understood or even tried? You may ask right at the outset, as I had to ask, how do we do spherical geometry in any sense? The Overview AI bot that has recently been installed by Google, which is my search engine, has informed me, remarkably for the first time in all of my research, of the concept of an extrinsic geometry. You may never have heard of that. If you know anything about spherical rotations, or even if you have studied to be a pilot, then you know that the Euler angles that are used to compute trajectory can be viewed either extrinsically or intrinsically, so the duality is by no means unknown or unused. In the case of geometry, I have never, in all of my research in this area, run across the expression or term extrinsic geometry or intrinsic geometry. But it turns out that it's a most natural dichotomy, as I have extended the use of that word. It actually can be used that way, but isn't often used that way. A dichotomy is my synonym for what is often called a duality. For instance, electroforce and magnetoforce are in dual. They're conjugal, as James Clerk Maxwell proved. In our tour of the universe, this will be unlike the previous tours of the universe that I've ever given, and I have given many in the early days. This will be going from outside in. So in order to prepare ourselves for a direct perception of spherical geometry at the universal scale, I'd like you to draw a circle and draw another circle inside of it. The scale will not be important. We're talking about strict spherical geometry. The reason we're using circles is that is exactly how we see a sphere. When we look at a sphere, we see a circle. And that makes perfect sense to us because the obverse side is blocked by matter. But in this case, the circle is transparent and you're actually looking at a sphere. You're looking at the profile of a sphere with an artificial circle to delimit what otherwise would be an invisible perimeter called a surface. And the reason I indulged in that seeming lemma is because it's the concept of a surface that produces what the AI engine calls intrinsic geometry or extrinsic geometry. And I looked it up in Wikipedia and noticed that it has changed since the last time I checked the article on spherical geometry, unless I overlooked a very short, it's just one sentence, that says that spherical geometry has been parameterized in two ways. One of them is extrinsic, and that's the only spherical geometry that has ever been formulated. But there's a footnote, as there so often is, that you can make a blanketing statement, but you have to be so cautious about an anomaly or an anomalous aspect or an inexplicable aspect or a zero or an infinity or some other part of what you're seeing that is easy to overlook if you don't concentrate. So a surface is a unique concept in geometry, but it has several aspects because of the way we've developed geometry due to our natural blueprinting and the natural form that we see of the universe in any aspect. These have to match somehow. That's called geometry. The service of mathematics, that is, of numbers, is in support of geometry because we don't learn anything from mathematics directly. There's a footnote to that goes on for volumes. But I'm currently not interested in that, although it's extremely well developed. This is the part of the relationship that I simply disregard because it's a human invention. That extrinsic geometry is the only geometry that's ever been used. But there is a group, that is a branch of mathematical physics, that does deal with intrinsic geometry, but it turns out that the way they themselves define the intrinsic framework is different from what Wikipedia describes or what the AI bot points out. There's not a lot of information about intrinsic geometry for the reason I just suggested. It's never been used. But there have been, or I should say there has been, a whole branch of mathematical physics that has attempted to simulate intrinsic geometry, which would be what? It only applies to a surface. By analogy, or analogy, however you may pronounce that word, analogy is how an American would pronounce it. By analogy, if you were to consider the Euclidean line, you could approach it extrinsically or intrinsically. What would be the difference there? In the case of the straight line, it's somewhat oversimplified because a straight line is not a surface. But you can start the way Euclid did by defining what you mean by the parts of a line before you state what is a line. This is how Euclid began. The first sentence in Elements is about a 0D point. Euclid did not explicitly use the term 0D, but what he said was it has no dimensionality. That is 0D. So it's a null point. So it has no meaning except words. But by beginning that way, he was able in his second sentence to state what 1D is, and that is his definition of a line. It's composed of points. When you say that, you've changed your definition of the line to a superposition where the line is simply an object, but the number system is an intrinsic part of the object. So in that sense, you could say the line taken as such, without a metric, but just as an object, is an extrinsic definition. It relies on the space in which the line is embedded, which must exist. In 2022, I was able to prove that any Euclidean line of any length, either in one direction, well, not in just one direction, it would have to be its full dual infinity extent, a plus and minus infinity. You have to say plus and minus if you want to get the numeric. This would be a charge relationship, by the way, in its extended use, that is, the polaric numbers that go in 180-degree opposite dimensions. We call them plus and minus numbers. That plus and minus is extended to electrodynamics. But you may notice, if you know anything about the Maxwell equations, that they don't use polarity. They use perpendicularity, and that is orthogonal to a straight line. And that's the relationship between electroforce, which is conceived as plus minus, and the magnetoforce, which is perpendicular to electricity. Maxwell proved that. Shortly after Maxwell proved that, Einstein was able to prove that a linearized version of time, which itself has no dimensionality whatsoever, it can be conceived as a straight line and then added to a 3D extrinsic definition of space. And this word extrinsic must now be added to our vocabulary because of what I discovered, which is not megalomaniac. It's simply logical. Because the sphere is a surface, and so it can be parameterized intrinsically. It never is, it never has been. But it has been claimed by a certain branch of mathematical physics that it has been explored and is currently being explored. That is an illusion which I will simply describe rather than prove it. Although a proof is extremely important, this is intending to get to another subject where you may just have to either take my word for it or check for yourself. But the sphere has always been approached mathematically and therefore, well, not therefore, but in our case necessarily so far, the sphere has always been approached with an extrinsic frame of reference in relation to the object itself, in this case a closed surface. A sphere is completely unlike a straight line, which means that it's outside the realm of linear algebra. However, we've learned ways to simulate curvature, that is, to explore it, to get its properties, and to compute it. You know that the major tool used for this is the calculus. And that is, of course, a monumental tool. But it's a tool that's been added to the mathematical system. It relies on a certain conversion method, which is highly interesting, I'll put it. The second tool that we've used, which has proved indispensable, perhaps in a sense even more indispensable than the calculus, although it looks like it's a tie, to get at curvature, in this case circularity. The calculus works on any curve or any curved surface. It can be extended even to 4D, as Albert Einstein proved. That's hypercalculus because it's a hypersurface. It's actually a cubic surface that's been extended into imaginary space, which is the term I will be dealing with in this brief presentation. Now we turn to the outside of the universe, which you now know, according to my research, this has all been rigorously proved. The universe can be said to have infinite extent. That's never been disproved. But we have to do something about that because infinity is incomputable. And therefore we must apply an edge. In other words, we have to delimit the universe spherically so it has an outer surface. But it would have to be imaginary, would it not? That can be done with super complexity that I discovered. And it's simpler than regular complexity. But it does use imaginary space. Imaginary space, curiously enough to say, is real. And that's where I want to begin. We are now outside the visible universe, you and I, each with our own craft or however you picture that, but we're actually gods. So this is not blasphemy, it's just a Gedanken experiment. We're looking at the visible universe from the outside. What do we see? We see a spherical surface that does not exist. It's simply where we're going to draw what we have to draw to compute the visible universe, disregarding the outside. That's called the outer product in geometric algebraic construction. And the outer product and inner product actually combine using I'll just say an operator, but an operator can be a function, as it is with a complex translator. It's a conjugate function. So it's not strictly speaking an operator, but it's used as if it were an operator. So for all practical purposes, it is an operator, but it operates between what we would call dimensions. In this case, we're looking at a spherical outer dimension, and we're inside the outer product, which cannot be reached by definition. This gives us a clue. We, you and I, in our position outside the visible universe, are by definition in imaginary space. Now, remember that you drew a circle and another circle inside of it. That makes 3 regions, does it not? The outside, the inside of the inner circle, and what is between the circles, which would be called in one nomenclatural system a spherical annular ring. Don't let that confuse you. It's just the space that's between the inner sphere's surface and the outer sphere's surface. Now that is going to end up being real space. That is what we would call 3D space that has depth. So it's volume space, but it has no linearity. So this is non-Euclidean. This is the pure non-Euclidean axiomatic basis of the system I discovered. I'm going to show you from outside in how to rationalize the universe without losing anything. And if one can do that without losing the infinities, and you see that I said plural, then that is perhaps, I'll just suggest, a major breakthrough in mathematics and geometry, and most likely physics, since that would be an exact match on everything that was discovered at the fundamental level in the 20th century. Namely, that the universe is spherical at all scales. It's spherical. That would be the correct geometry to use for physics now, since we know what we're looking at is not linear, it's spherical. That's actually the basis of my original hypothesis. This was the second step in my discovery, or the third, and you could extend it because this is a steeplechase, actually a fish ladder, of paradoxes that have to be solved to get to the place that I'm starting you at. So you're going to see the sequence from the outside in. The first thing that one does in being in this godlike position of being in imaginary space which cannot be reached. It cannot be reached by human perception. It cannot be reached by mathematics, except that's exactly what we're going to do. We're going to use mathematics to parameterize the universe, not just the visible universe, the entire universe, both imaginary and physical. It's hard to... the word real is a little overused, so let's just use it in a new context. The real universe, as opposed to the imaginary universe. That's the definition of complexity, if you can combine them. Here's how you can combine them into component space. We are in imaginary space. Now we're going to switch just for a second, because we're bipolar creatures. We can shift our field of view from looking at the whole universe from the outside, which is a sphere, and now transfer yourself to the center of that sphere. The universe as we've computed it so far has no such center. It appears to us as if the entire universe is its own center, which is a paradox. So now put yourself at the center and look out in all directions at once. That's pretty easy to imagine, although your brain probably cannot do it. You can tell your mind to do it. Now what you see is the surface of the universe from the inside, and it has a very small limit. We're inside the atom, but it's not the atom of Bohr. It could be considered the atom of Democritus, but in this case, I don't know if anybody has ever conceived this kind of a particle. It would be a unique particle. The center of the universe which is empty, we're going to say. So the center of the empty universe is imaginary, and it has a radius, so you are in imaginary space looking out to a surface. Now switch back to the outside. You're looking at the outer surface, and the center surface is a sphere, but it has no interior, to the same proportion that the space outside the universe is also imaginary. So these are two infinities that have a geometric relationship that I discovered. It's a mathematical relationship between the center point and the edge. The center point is a sphere with no interior, and that changes the Euclidean definition of a point. In this universe, there is only one point. That point that has no interior, but it has a spherical surface. How do we know that? Here's how. You now invent a number system with two fractions that multiply to 1. These two fractions are called reciprocal fractions. And the definition of the reciprocal fraction is that with its conjugate fraction, they always multiply to 1. We're going to establish another axiomatic statement, which is that all of these fractions are based on unity, such that in one of the two conjugate numbers, these are fractions that are reciprocal, on a diagonal is the number 1. So the number 1 is the denominator of one of the two conjugate fractions, and the other number is its reciprocal, transferring the 1 to the numerator. And then the other number on the other diagonal is a single number. It would have to be, this would be a whole number, so that's another axiomatic statement, that one of the 4 numbers is a 1 on a diagonal, and the other number is any other whole number. Thereby you have conceived a new number system that's not based on 0, as is the straight line. The straight line is based on the center number. In the spheric number system, the center is defined as the surface of the inner sphere. So the inner sphere has a number. It's the number 1. How do we know that? Because of what we're going to do now by defining the center and the edge. The center is inside the 1. And we're going to say that that is imaginary space, and we're going to say that what's outside the outer circle, outer sphere, is also imaginary, but we're going to compose these two numbers in the reciprocal fractional system so that they multiply to 1. And now you could probably guess it's fairly easy. Lazy 8 we define as spherical infinity, and we put it outside, so that the entire universe that we refuse to be able to see, since we cannot, we simply artificially make an edge, and we give it a number that is a fraction. And that is a proportional number, as you probably either know or can figure out. So it's infinity over 1, and that's perfect visually. Just writing it, lazy 8, line 1. That line is the edge. What's inside it is the number 1. So that's the universe is 1. The entire inside is 1. The outside is imaginary. It's imaginary infinity. The reciprocal of that number defines the center. 1 over spherical infinity. Proportionally just as imaginary, but at the opposite end of the spherical force line. That gives us the definition of the center. It is a spheric surface with a value of 1. We now know the value at the edge as well. Notice that it's only the surface of the inner sphere that has a value of 1. That is the intrinsic mathematical definition of a sphere, is that it has the value 1. And that 1, represented by exactly one of these two numbers, the larger of the two, which would be, for instance, 2 over 1, makes a concentric sphere going out. But this sphere is only one of the component numbers. So all of real space is represented in concentric rings going to the highest number. The lowest number is the surface, and so the lowest number in the natural universe, the way we're composing it, is 1. Therefore, anything less than 1 is imaginary, and that is the intrinsic definition of the ball. It's purely imaginary, because what's inside the surface is less than 1. But the surface is the equivalent of linear 0. You might say, well, then we don't use it. In the same way we don't use 0. But it needs to be there. That 1 needs to be there. That 1 is the quantum. That is a strict mathematical definition, by the way, of quantum. That is exactly what quantum should mean. It means that inner sphere that has no interior. The inside is reciprocally equivalent to spatial infinity. So the question would then be, is that space inside at all? Yes, because it's space outside as well. But it has a unique property not shared by any other space. The outside of the visible universe is one imaginary number, defined as that number in the system that is larger than any other number, and that is a unique number in imaginary space, but it's one number. This is, in my mind, this is the trickiest part. But we do need to somehow conceptualize imaginary space. So we're going to do it dually, so that it defines itself by reciprocating itself to unity. And so the definition of infinity is when you multiply the number that's smaller than any other number, that is imaginary, with a number that is larger than any other number and is also imaginary. It does the same thing as all the other pairs of numbers that multiply to 1. Namely, they multiply to 1. Where is the infinity then? Because it has to be characterized in some way perceptually. Otherwise, it doesn't ultimately make sense to us. Well, that's the glitch. That is truly the definition of imaginary space. It is that which we cannot conceptualize either with numbers or with geometry or with perception. So it's a triple paradox. The solution is to make it cancel itself so everything else is rational. That's what this does, and here's how you can see that. Since the edge is infinity over 1, from our perspective, the edge itself is infinity. And that's the largest number. The smallest number we discovered is at the surface of the inside of which is imaginary space. That makes the inner surface invert in its valence, because in the case of the surface of the inner sphere, it is the surface that is 1. In the case of the outer number, the surface is infinity. And that's two different intrinsic parameterizations. They're reciprocal, so they're logical. And so two paradoxes cancel when you do this. And what it leaves is quantum space, with a center that is the quantum of some force. This is the Bošković discovery. And I'm adding that now, although that could confuse the you-know-what audio. This has baffled every great mind that's ever lived, including Einstein and Dirac. So what they missed, because they didn't see it, they didn't see this mathematical trick, that if you use a two-component number to parameterize the sphere, if you choose the inner sphere to parameterize, you can do so on two numbers, such that they multiply to 1. And so we have the parameterization of the quantum sphere is 1 over 1 times 1 over 1. And that's the only sphere that has the value 1 in all of its numbers. That has been proved to be light speed. And that will end this brief, incomplete introduction to the axiomatization of universal space using hyper-imaginarity. In the next lecture, I'll introduce you to hyperspheric space, which I've attempted to introduce several times over the past 30 months. But I think you will find out, if you choose to tune in, which I hope you do, you'll be rewarded, that hyperspheric space is the solution. It leads directly to the theory of everything, which has several aspects, because everything obviously is an overblown word in the term. What we're actually looking for is a two-force balancing system that describes universal dynamics. That was discovered in 1758 by a Jesuit priest, the greatest mathematician in Europe at the time, because he lived in between the time of Leibniz and Newton, who had just died, and somewhat before the time of Euler and Gauss, who were older than Bošković. And I hope you tune in for the remainder of this. Through Thanksgiving, I will be giving you the theory of everything, mathematically and geometrically, and the trickiest part is perceptually, so that you will be able to see the universe dissolving all the theories that have confounded science for a century. You will see past the conundrums and paradoxes of the quantum paradox. And once again, as I have done many times before, I will show you what it means to collapse the wave function so that you'll see it, and it will make sense, and you can compute it. Stay tuned. This is Galactic giving you the secret of the universe. No longer the byline. We've got it. Keep looking up. Stay tuned.